Okay, today we're going to find the equations of tangents and normals. Equations of tangents, that's an O, and normals. Not plus normals, but and normals. You know what I mean. Okay, equations of tangents and normals. Let's start with a function. Let's call it y equals, start with one of these ones again, 5x over the square root of 3x squared plus 2. Okay, I stuffed this one up, a similar one in my last video, so I thought try and redeem myself a little bit, hopefully, if I don't bugger it up again. Okay, so dy dx, we need to do dy dx. Okay, so we're going to use quotient rule. So the thing I do with quotient rule to make sure I get it right is I square the bottom term. So I just end up with 3x squared plus 2. Okay, then I put the original function up here. So I'm going to go square root of 3x squared plus 2. Okay, and then times the derivative of the numerator. So that's 5 minus, and I'll do the opposite of that. So I want 5x multiplied by the derivative of this one. Okay, so this is going to be 1/2 times the derivative of the inside, so I'll make that 6x. So that's the derivative of the 3x squared, the 6x. So the half is from the square root coming down, and then I get 1 over the square root of 3x squared plus 2. Okay. All right, so instead of using index notation, I've used the square root notation, and we can simplify this by putting this over a common denominator. So this has got a denominator, all of this, of square root this, so I want this to have the same denominator, so I'm going to multiply it by square root 3x squared plus 2. So that's going to give me 3x squared plus 2 multiplied by 5 divided by the square root of 3x squared plus 2. Hopefully that's not too small. Okay, so this is over a big 3x squared plus 2 minus, what's this? This is 3x times 5x, so I've got 15x squared over 3x squared plus 2. Okay, so this denominator, this common denominator, can come down into this line, and then I've got 3x squared plus 2 to the half, right, times 3x squared plus 2. So that's going to give me 3x squared plus 2 to the 3 on 2. Okay, so let me put that in. I'm just wondering where the best space to put this is, because I'm running out of room. So let's put the denominator here. We'll go 3x squared plus 2 to the power of 3 on 2. Okay, so that's the combination of the common denominator here. Yeah, putting this all down into one line. And then I've got 15, if I expand this out, 15x squared, but then I've got minus 15x squared, so that's actually going to cancel with that one. And then I've just got 10. So I've just got 10 over this thing. I think that's it. Look how good that is. That's great. Okay, so remember that. I might rewrite that. I might rub all this out and rewrite it. Okay. So hopefully I didn't make a mistake that time, and we've got it all right. So I've got this. I've got dy dx equals 10 over, we could put it as a square root of 3x squared plus 2 cubed. I can put that in there. Yeah. Okay. So let's find the equation of the tangent. Let's make it at x equals 0. So at x equals 0, we know that y equals, what's y equal? So I get 5 times 0. So we're going to get 0 here because I get the 0 on the numerator. We'll just make sure that the bottom doesn't equal 0. No, it doesn't. It equals 0 on root 2, so that's good. So y equals 0. What about dy dx? And dy dx at x equals 0 is 10 on, what's this? 2 cubed to square root of 2 cubed. So 0, so we get 2 cubed is 8, square root of 8, so that's 2 root 2. Okay, which is the same as 5 on root 2, which is also the same as 5 root 2 on 2. 5, 2 times root 2, if you like. Okay, that's great. What does that give us? We've got a point, so we know a coordinate. We've got x equals 0, y equals 0, and we know the gradient at that point. So if we know what a coordinate and the gradient at that point, we can use, because we know we want a straight line, y minus y1 equals m tangent of x minus x1. Okay, so now if I put this information in, so I've got y minus y1, which is 0, m, which is 5 root 2 on 2, x minus 0. So the equation is just y equals 5x root 2 on 2. That's a weird way to write it, but that'll do. Okay, I think that's it. Okay, why did I do that? I don't know why I do these silly things. Let's put the x out there. 5 root 2 x on 2. There we go. Okay, so that's the equation of the tangent. What if the question asks for the equation of the normal and not the equation of the tangent? So this is the equation of the tangent at x equals 0. Okay, what about the equation of the normal? Okay, so there's not much different. All right, to finding, there's just one extra step. Instead, I would just want to change this to, because the point is going to stay the same, but I want the line that's 90 degrees to this tangent line. So m perpendicular is the negative reciprocal of the gradient of the tangent. So I just take the negative reciprocal of this, and that's it. So let's take it back to here. So it's going to be negative root 2 on 5. So I just go y minus 0 equals negative root 2 on 5. Okay, so that's the negative reciprocal of that one. X minus 0, because x equals 0 at this point. So I've got y equals negative root 2 on 5x. And that's it. That's the equation of the normal at that point. Now, often you won't have 0 and 0. This is a very convenient one, and I'd have to do some rearranging, and that's fine. You just put them in. If this was 1 and this was 5, you put 5 here and 1 there, and you'd expand it, and you get an equation, y equals mx plus c, and you're done. Yep. All good. Okay, last thing I just want to point out quickly, the average rate of change. So these are instantaneous rates of change at those points. What about average rate of change? Sometimes you might get a question that asks you about average rate of change. Rate of change. And this is simply just graphing the gradient, yeah? Like finding the gradient between 2 points. So if you have some function x, y that does that, and you're asked to find the average rate of change between when x equals this and x equals this, we just want the gradient of the line that joins those 2 points together. So this is an x1, y1, x2, y2. So the gradient average, or the average gradient, is just y2 minus y1 over x2 minus x1. Okay. Now, you've done plenty of that before, so there's no need to do a further example of that, I don't think. It's just something to keep in mind when it's talking about average rate of change. It's just the gradient of the line that joins the 2 points. That's it.